Hello, and welcome to the lecture on energy transformations. So what is energy? Energy is the ability to do work. Energy produces light, heat, motion, sound, growth, and energy powers our technology. My computer is powered by energy. It's the ability to do work. Energy what gets us out of bed in the morning. So work is the force applied to an object times the distance moved in the direction of the force. So when we think about energy, because of the direct connections between energy and work, energy is measured in the same unit as work, which is joules. In addition to using energy to do work, objects gain energy because work is being done on them. So when we think about power, power is the rate. It's a rate, so it has a time unit. It's the rate at which energy is transformed or delivered. So when we think about energy units, we have joules, which is defined as the energy exerted by a force of 1 Newton to move an object 1 meter. We have BTUs, British thermal units, which is the energy required to raise 1 pound of water by 1 degree Fahrenheit. We have a calorie, which is the quantity of heat to raise 1 gram of water by 1 degree Celsius. And again, through unit conversions, all of these are related. When we think about energy, again, we're talking about calories, joules, BTUs, feet, pounds. And we think about power, we're talking about watts, kilowatts, megawatts. And a watt is defined as a joule per second. So if we look at this 100-watt light bulb, it provides power at the rate of 100 joules per second. The energy provided in 1 minute from this light bulb is 600 joules. So again, power is energy per time, which is joules per second, which is a watt. So when we look at our home energy bill, we can see that for our electric service, we get our home energy use in kilowatt hours. So that is an energy, that's the total amount of energy provided, okay? We also get our gas bill, for example, in cubic feet, which is converted to, in the US, which is converted to therms, which is, again, an energy unit. So therms is actually 100,000 BTUs, which is the approximate energy provided by burning 100 cubic feet of natural gas is 1 therm. So here we have 126 therms, which means that about 126,000 cubic feet of natural gas were burned to provide that heat energy to this house. Again, if we look at it, kilowatt hours equals power times time. And so it's energy times time divided by time. And so again, kilowatt hours is an energy unit, while kilowatt itself is the power unit. And this has a little example of that. Again, 1 kilowatt equals about 3.6 megajoules. 1 kilowatt hour, excuse me. 1 kilowatt hour equals 3.6 megajoules. So again, a kilowatt hour is an energy unit. So there's 5 main forms of energy. There's heat, chemical, electromagnetic, nuclear, and mechanical. And we'll go through these very quickly. So heat energy is the eternal motion of atoms and it's basically moving particles produce those energy. It can be caused by friction, and heat energy causes changes in temperature and a phase of any form of matter. Chemical energy is required to bond atoms together, and when these bonds are broken, energy is released. So again, gasoline is a form of chemical energy, food is a form of chemical energy, and they're basically stored chemical energy. When we combust that fuel, when we burn gasoline, that energy is released. Electromagnetic energy, again, power lines carry electromagnetic energy into our home in the form of electricity. So light is also a form of electromagnetic energy. And each color of light actually represents a different amount of electromagnetic energy. And again, it's also carried by X-rays, radio rays, and laser lights. Nuclear energy, the nucleus of an atom is the source of nuclear energy. When the nucleus splits, which is fission, nuclear energy is released in the form of heat energy and light energy. And nuclear energy is also released when nuclei collide at high speeds and join, which is fusion. So the sun's energy is produced by nuclear fusion reaction, in which hydrogen nuclei fuse to form helium. So you have two hydrogen atoms, they fuse together to form helium. Again, there's a further information on how the sun emits energy can be seen here in this YouTube link. Mechanical energy is when work is done to an object and it acquires energy. So the energy that requires is a mechanical. So when you kick a football, you give mechanical energy to the football, which makes it move. So when you throw a bowling ball, you give it energy, and that bowling ball hits the pins, and some of that energy is transferred to the pins, which is the transfer of momentum. So if we think about the laws of conservation of energy, energy can't be created or destroyed. It can only be converted from one form to another. But if energy seems to disappear, then we kind of look at what's happening. And that's when we talk about heat energy, heat loss, and different forms of transformation of energy. So when we look at a basketball, for example, and if we're throwing a basketball, at the top, the basketball has the maximum potential energy, but then as it comes down and it speeds up, it has the maximum mechanical, kinetic energy. So we have potential energy and kinetic energy. And when we talk about energy transformation, so for example, when we're looking at the sun, the nuclear energy in the sun going into plants, that then over millions of years, the formation of fossil fuels was created coal, then that coal, that chemical energy is then burned, and we have heat energy that's produced. That heat energy turns a turbine, which is mechanical energy. And in that turbine, we have a generator, which has magnetic energy, which then creates electric energy to power our television. So again, it's conversions between all of these forms of energy. So if we think about potential energy, stored energy, so we can have potential energy stored in bonds. So gasoline is chemical energy that can be used, that's stored in the chemical bonds. We have mechanical energy stored, potential energy stored in mechanical, so like a spring. So as soon as you release it, that's there, so that's potential. We have, again, it's stored in the nucleus of an atom, is potential energy in nuclear. Gravitational, again, hydropower takes advantage of the difference in height between where the water is and where it's going. And so we tend to put hydropower on dams that have large potential energy between where it's coming and where the outlet is. And that's how we get hydropower, is that potential energy. Also in electrical energy, lightning and actually batteries is the storage of potential energy in the form of electricity. Again, it's stored again in fuel, nucleus of atoms, and food, or stored because of work done on it, the stretching, the pulling back of an arrow, the lifting a brick high in the air. We create a potential energy in terms of gravitational energy. And potential energy is dependent on height is called gravitational potential energy. And so again, when we look at gravitational potential energy, it's the change of raising an object is equal to the work done by raising it. And this is the potential energy. When we think about roller coasters, so when we start out on a roller coaster, we have maximum potential energy at the start of the ride. And then you get maximum kinetic energy just as it passes through the bottom of the loop. Right here is our maximum potential energy. And then we have each loop is going to be a little bit lower than the one before because it's going to lose energy from friction, from heat as it keeps going. And then we have centripetal force provided by the track pushing against it, allows it to loop the loop, and then it has less energy at the end due to friction and air resistance. Kinetic energy is our energy in motion. So the faster an object moves, the more kinetic energy it has. And the greater the mass of moving objects, the more kinetic energy it has. So it depends both on mass and on velocity. And so when we look at kinetic energy, it actually is half times the mass times velocity squared. So it's directly proportional to mass, but it's actually double mass equals double kinetic energy. And decrease the mass, you would decrease the mechanical energy in the same way, but the velocity is actually squared. So it's actually a much more important parameter in terms of changing that. So if we look again, if a velocity is 5, we're going to get 1200 joules of kinetic energy. But if we double that, we get more than double. With the mass stays the same, we get 5,000 joules. And again, with the velocity being 10 meters per second, we're going to get 20,000 joules because of the squaring of that velocity term. Electrical energy, again, is the forces between atoms. And so with the electrons detaching from the atom and moving, and it requires input energy due to the loss of energy from collisions. And then voltage is going to be the difference in potential. So again, when we look at potential energy versus kinetic energy, and these are the equations that we're going to be using, you can see that, again, potential energy is the force times the distance, which is mgh, mass times gravity times height. And again, weight is the mass times gravity, and then times the height. So we have kilograms. If you look at meters per second, meters, this is the gravity. That's the units for gravity. So 9.81 meters per second squared is actually the unit for gravity, times the distance times the meters. So again, kilograms times 2 meters, squared, divided by second squares equals joules. That's the unit for joules, and that's our potential energy. If we look at kinetic energy, again, kinetic energy, we said 1/2 times the mass times the velocity, meters per second squared, equals that same thing, equals joules. So again, we can connect potential energy to kinetic energy. They have the same units, which is joules, the kilogram, meters squared per second squared. So if we look specifically for wind energy, if you look at kinetic power, so you have 1/2 times the air density, which is our mass, times the blade of the coverage, so that's our area, times the wind velocity, and it's actually cubed because, again, we're just using the area and we're having the meters per second because every second that much area is going to pass by the wind. If we think about power here, again, it's a per second. So it's, again, now we're going to a power basis. So our power here from kinetic wind, our power here from potential energy is going to be G times the flow times the height times gravity, okay? So now instead of just thinking about the mass, we're gonna actually use, again, a second per second. So it's gonna be our flow rate in meters cubed per second. And that would be our power equation versus our energy equation. So going through our laws of thermodynamics, the 0th law is that if A and C are each in thermal equilibrium with B, then A will also be in thermal equilibrium with C, okay? If we look at our first law, it's that energy can be transformed or changed from one form or another, but cannot be created or destroyed. So again, the change in internal energy might be the heat added to the system minus the work done by the system. So both of those together will equal the change. Our second law of thermodynamics is it's impossible to extract an amount of heat from a hot reservoir and use it all to do work. Some amount of heat must be exhausted to a cold reservoir. And so if we think about, all engines coming to an environment, there's going to be an efficiency, and we'll talk a little bit about that Carnot cycle and the maximum efficiency that we're able to achieve. And so extracting all of the heat and using it all to do work would constitute a perfect heat engine, which we can see from the second law is not possible. So when we think about, again, we went through this again, but we're going to think about this, understanding electricity and the electricity process is really important. So again, as we said, we start with nuclear energy, and then we go to radiant energy, which is number 2, which is our sun, which then goes to chemical energy, the bonds of the food, right, that's stored. And then that chemical energy is stored both in the food and in the coal that took millions of years to process. Then that coal is then burned and we get thermal energy. So again, both the thermal energy in the boiler as well as the steam is our thermal energy. And finally, we have our energy of motion in 7 as the turbine moves. And then finally, from the magnetic energy, we get from the magnets and the turbine, which we're going to talk about how that's formed, we get our electric energy. So we're going to concentrate on this electric process now. So again, producing electricity, we can get it from oil, from natural gas, from coal, from nuclear, or from various renewables. And those are the primary sources. And then our secondary source is going to be our electricity, which we can use for heating, cooking, air conditioning, lighting, refrigeration, information technology, electric motors, etc. So what is electricity? So electrons in the shells closest to the nucleus have a strong force of attraction to the protons. And sometimes electrons in the outermost shell are not held with a strong force and can be pushed out of their orbit. Applying a force then can make them move from one atom to another. Those moving electrons are electricity. They're moving electrons that are forced out. So when we have spinning of electrons around a nucleus of an atom, creates a tiny magnetic field. But most are not magnetic because the electron spins in random directions and kind of cancel each other out. But magnets are different because electrons spin in the same direction, creating two poles. And so moving magnetic fields can push and pull electrons, which actually produces electricity. And then we create this flow of electrons in a metal wire. And we'll talk about copper wire and why we use that. And so again, we see that the opposite poles attract each other. And by moving that magnetic through, we're actually pushing and pulling electrons. So that movement of the turbine with the magnet is going to push those electrons out, and that's our electricity. So if we look at a generator, this is a turbine generator. So again, the turbine can be moved by water for hydropower. The turbine can be moved by wind with wind power. The turbine can be moved by steam, and that steam can be produced by bioenergy. That steam can be produced by coal, by natural gas. It's various ways we can get, all we're trying to do is move a turbine, right? Solar PV is different, and we'll talk about that. But the rest of them all deal with the same technology. It's this turbine generator. And so what happens is, again, you see we have a spring of coils here, and we have a turbine that we have the turbine that all it's doing is moving the shaft. Okay, that's the important part. And it's moved around a magnet. So converting mechanical energy into electric energy with any power plant, no matter what we're doing to turn it, whether it's hydropower, wind power, coal, natural gas, we basically have a large magnet that spins inside a coil of wires. And high pressure steam, water, anything acting against the turbine blade spins this magnet, and the flow of electron is produced as the loops of the wire rotate between these magnetic poles. And then the current is ready for transmission and distribution through our power grid. So we have conductors and insulators. So conductors are materials with little resistance to flow of the electrons. So again, copper wires, they have very little resistance, and so they're going to flow through. So here we can see the copper wires inside, and little energy is needed for electric charge to flow through these conductors. And so most metals are very good conductors of electricity. Now the insulators, this is going to be our outside. So they have a lot of resistance to the flow of electrons. So they allow very little electric current through it. So this is where we're going to use plastic or rubber on the outside of the electric wires to keep the electricity inside, because they're not going to convey that electricity. So again, metals are really good conductors of electricity because they have free electrons. So here's our positive ion and our free electrons. Each atom releases one or two electrons, becoming an ion. So a piece of metal is a lattice of ions through which electrons are constantly moving in random directions at very high speeds. And so our copper wire has one lone electron in its outer shell, which can easily be pulled away from the atom, and electrons move from atom to atom to atom in a wire, and that is what's producing our electric current. And so again, going back to our steam power engine. So again, here we have a steam boiler. So we have our fuel, let's say coal, natural gas, and we have air. And we have flue gas and fly ash that's produced. This high pressure steam goes through our steam turbine, turning a shaft, which is connected to a magnet, which produces our electricity. And then we have a condenser where we actually condense it with steam here. We condense it back down to water. We pump it back into here, and then we use more fuel to heat it up again. We also have internal combustion engines. And so we have different engines again, being an air fuel mixture. We have our cylinder and our piston here. And there's different ways we can actually connect these fuel mixtures in these internal combustion engines. We can have an induction stroke, a compression stroke, a power stroke, or an exhaust stroke, which is just different ways of powering this air-fuel mixture inside the combustion chamber. Again, when we look at the Carnot diagram for a heat engine, so any of these heat engines, we have a boiler and we have our input heat into our heat engine, and then we have our useful work that's making our car go forward, for example. But then we also have waste heat, and then we might have a condenser that's, again, moving these things through when we look at our electricity generation, for example. So the first law of thermodynamics is all of our energy is conserved. So our work, our useful movement, is going to be the heat in the boiler minus the heat loss. And so our efficiency is our total work divided by the heat that's actually transferred in the boiler. And so we can rearrange this with the work here divided by Q1. And so we get 1 equals Q2 divided by Q1, with Q2 being our heat loss. And so we can also look at this efficiency based on temperature. And again, we can look at our temperature 1, our useful temperature, minus our waste temperature divided by our useful, our temperature raised, is again going to be our efficiency. And finally, when we talk about heat pumps, so again, heat pumps are used in refrigeration. So again, we have our low pressure evaporator. We have a heat source here that actually has cold vapor that's produced. And in our regular domestic refrigerator in our kitchen, we have a compressor, and basically electricity runs that compressor, which takes a hot vapor, and we have a heat sinks, which then condenses the warm liquid back to the cool liquid through the evaporator, and the cycle continues. So this is what we actually have to have a power source to run this, and this is what we do in heat pumps in our refrigerator. Well, we do the same type of thing when we're talking about heat pumps when we think about geothermal energy, for example. So what we're doing is we're just using heat differentials, right? Something from a low pressure to a high pressure. Similar in a geothermal, what we might have here is a heat pump, okay? But in this heat pump, we're going to use a deep loop in a deep borehole, or we can have a shallow one. We can have different types of geothermal systems. And basically what we're going to do is use that heat differential. And so in the summer, this deep borehole down here, this is going to be much cooler than our house, right? And so in the summer, we're actually going to use that heat pump to actually bring that colder air up, and we're going to use it to cool our house and bring the warmer air down to keep that heat pump going. And in the winter, it's going to be the opposite. Up here is going to be much colder than here in our ground. And so we're going to be bringing this warm, in the winter, we'll bring warm air up to heat our home, and then bringing the cold air down. And so again, we can actually tap this into our existing radiator, space heating, hot water, so that again, it's more of we can either use it as our only heat, or we can just use it as an energy efficiency process where we're basically bringing in the temperature at a higher level or lower level, higher level in the winter, lower level in the summer. And so that we are increasing the efficiency of the system by using the same concept we use for refrigeration, the heat pumps, but using it based on the ground temperature. All right, thank you very much.